In this example, we're going to try to find the weight of that box that can be moved with that 10 kilonewton force shown in the top right. So instead of finding perhaps what the force to be able to move the box, we're going to try to find the weight of the box that can be moved with that 10 kilonewton force. To start the problem, I need to make an assumption whether or not the box is going to be sliding or the box is going to be tipping. Because depending on that assumption, we need to do a different free body diagram. So in this case, I'm going to make the assumption of sliding. That's going to be my assumption. Based on that assumption of sliding, now I can do my free body diagram. And my free body diagram is going to be something like this. That's my box. I'm going to have a weight here, which is unknown. I don't know my weight. I do know the force that is pushing is 10 kilonewtons. And since my assumption is sliding, I need to have my normal force towards the left-hand side of the middle of that box because I'm pushing from right to left. So my normal force is going to be somewhere in here. And the distance between my W and my normal force, I'm going to call that X. In addition to that, I'm going to have my friction force, right? And my friction force is going to be, I'll try to do something like this, see how it looks. That's going to be my friction force. I think that's it. That's all that I'm doing. Now, I made a mistake in there. Friction force should go in the opposite direction. Okay, sorry about that. Should go towards the right. So let me make that friction force red. It's an unknown force, right? Friction force to the right. Why towards the right? Because it should be opposing the 10 kilonewton force, which is going towards the left. I do not know my W, right? I don't necessarily know my normal force. And I do not know X. Okay, so we have 1, 2, 3, 4 unknowns. 4 unknowns, so we should be able to find 4 equations to be able to solve this. All right, very good. So I'm going to start with my equations of equilibrium. And I'm going to add one more equation because we know that in the case of sliding, my friction force is equal to that mu s times n. So I'm going to start with an equation that is the sum of the forces in X. If we are in static equilibrium, because it is about to move, it's not quite moving yet, right? So if that is equal to 0, we have that my friction force, oh, I need to put my X and Y axis, right? So let me put them over here on the side. X and Y. Pen is not behaving today. There you go. And so we have that that's going to be my friction force minus my 10 kilonewton force. That's equal to 0. So my friction force is 10 kilonewtons. One thing that's not my final answer, but that's one important number that I need to start remembering. Okay, the other equation I have is not an equation necessarily of equilibrium, but we know that our friction force, because we made the assumption of sliding, the friction force has to be equal to mu sub s times n. We have mu sub s, which is 0.3, right? Those coefficients of friction have no units. So from here we can say that my normal force is going to be equal to F over mu sub s, which is equal to 10 over 0.3. So So my normal force is going to be equal to 33.33 kilonewtons. That's a pretty big box for that force, but all right, very good. So now we have our friction force, we have our normal force, and what we need to do now is to, find our W, and we can do that by doing our sum of the forces in Y, right? So let's do sum of the forces in Y is equal to 0, and that will be equal to, we have the normal force, and we have the weight, okay, no problem. So my weight is going to be equal to 33.3 kilonewtons, right? 3 significant figures for my final answer. Now, you might find an answer, but what we really need to do is we do need to check on that X. That X has to be under the box, right? So to be able to check that, we need to do some of the moments, and we can do some of the moments somewhere in that box, okay? So let's see, the easiest way might be to make the sum of the moments where we cancel forces. I'm gonna put it here, this point in yellow, right? I'm gonna call that point in yellow where the interception of the friction force and W, I'm gonna call that A, just to give it a name. And I'm gonna do some of the moments about A. So I'm gonna do it here at the bottom perhaps. I'm gonna do the check. So some of the moments about A have to be equal to 0. The reason why I chose that point is because then I have less forces to worry about. I don't need my friction force. I don't need my W. Only thing I need to know is N and the force that is pushing. So in the case of my force that is pushing, let's go back all the way up. That is 2 meters high, right? 2 meters high. So it will be 10 times 2, and it's a positive moment. Right? I should probably put the fact that this is 2 meters in this direction. Okay, so this is 2 times 10, and then my normal force is creating a negative moment about A, and the moment will be N times X. So minus NX. So from here, we can say that X is going to be 2 times 10 over my normal force, which is 33.33. So I get that X is equal to 0.6 meters. Okay, 0.6 meters. How do I check this? Well, let's look at the top diagram. The width of that box is 1.5 meters, which means that half of it is 0.75 meters. So since this is 0.6 meters, is less than 0.75 meters. So let's check. We're good. That means that the weight really is 33.3 kilonewtons. If the X will have given me, let's say, 1 meter, that means that that normal force was outside the box, which is not physically possible. And then I have to change my assumption from sliding to tipping and redo the problem.